Hello, Professor. I hope you are doing well. Today, I'm going to talk about the first assessment. Let's start with the first question. Here, I'm using an image of the internet that I found about my computer. It's a Core i7 Intel 12700. So, this chip has 14 cores, which is huge. And in these 14 cores, I have in my own computer 6 performance cores and 8 efficient cores. I found that what the difference between them is just the performance cores are some cores done for heavy tasks like playing video games, and for the efficient cores are some cores that are here just for to handle lighter background tasks with minimal power. And also, I found that the processor is called the Intel 7 because it refers to the size of the transistors being around about 10 nanometers in this Core i7 that I have. So, shrinking the transistors make them faster and more powerful, uh, and extremely efficient, and make them pack in into one single chip. So this directly leads to more powerful and complex CPUs. So here, when the number of the transistor increase, of course, there is a limit to the Moore's law, and we cannot go further and further in the increase in the number of transistors because physically it's impossible. A transistor is made of silicon, and we cannot go beyond an atom of a silicon if we want to make more transistors. So basically, there will be a limit and an atomic limit, and we have to find another material, a new material, to fix this problem of the number of transistors in the future. But before that, let's understand why we moved to multi-cores. Why we didn't only stay with one single core and make it faster and faster. Why did we move to multi-cores? And what are the benefits and what are the advantages that offers the multi-cores? So the first inconvenient with a single core is the power hit. Making one single core faster and making it extremely high in speed increase the hits of the core. And if the heat increased, then it will overheat, and if it overheats, then it will just gonna make the processor go slower again and again. So this is what we call the the power wall, which is basically the wall done by the heat, the overheat. So instead of making one single core extremely powerful, engineers start doing multiple cores, slightly, not a lot less powerful, but slightly less powerful than an extremely powerful core, and they called it multi-cores, so they can control first of all the problem of the heat. So to relate this to my CPU, my own CPU, so my own CPU use a hybrid design. As I said before, the performance cores that I have handle the demanding task like what I'm doing now, recording or doing some task like gaming and editing, like I'm going to edit this video, while the efficient cores take care of the background task, and this helps my computer save a huge amount of energy and power, and this goes directly inside the CPU. So for the von Neumann model, before this model, the computers before were built separately, the memory for programs and the data which was rigid. So basically, the Van Neumann is a single thing. It's a single concept where we use a single unified memory for both a program instruction and the data. So, for example, let's take an example of a mixer. So, a mixer is not a Van Neumann model. Why? Because a mixer can only do a single task, one task, because it has a closed circuit and it doesn't include a chip. Why it doesn't include a chip? Because a chip is too expensive. So instead of, for example, buying it with 200 dirhams, we're going to buy the mixer with 2000 dirhams. And now we can code the chip and make it do more than only one task. And it will become a Van Neumann model machine. So now I'm going to use this small schema to introduce how a CPU can do the fetch decode execute cycle. And now with the example that you gave us, let's trust the steps of the add 100. So always it's going to start with the fetch, if there is no interrupt, of course, but let's assume that it starts with the fetch. So the CPU has a tiny and a super fast memory inside. It's called the program counter, the PC, which is here. So the PC holds the memory address of the next instruction to be executed. It's storage. The CPU sends this address to the memory via the address buses, and it says, for example, go to the shelf number 50. The memory retrieves the address add 100 from that shelf and send it back to the CPU on the data bus. So the CPU stores this instruction in another internal temporary storage area in the instruction register, which is here, the IR. And finally, the program counter increments the point by one. So the PC will be now one, incremented by one, according to what value it has before. For the decode part, now the CPU needs to understand what do we mean by this add 100. What does it mean? So the control unit inside the CPU decode the instruction. Here the control unit is decode the instruction, and it recognize the add, which is an arithmetic operation, and the 100 as the data going with this instruction. So it now knows it needs to get the value 100 and perform an addition with the current value in the accumulator. So whatever value we have in the accumulator, we know the CPU knows that it had to add this 100 to this value. And accumulator it's basically a specific register used for arithmetic operations, like the case we have now. And now for the final stage, which is the execute stage, the phase. The execute phase happens in two parts because of the Van Neumann model, as we discussed previously. So first of all, the CPU might need to fetch the operand, which is the 100 in our case, and it is the data. It may need to send to another request to the memory to get the value 100 from the specific location where it is. So it needs to send, as I said, another request to the memory, and through the address bus, of course. So secondly, the arithmetic logic unit, which is considered as, in our case, the brain of the CPU, is activated, and it takes the value from the accumulator that we have. And the value that we have here in our case is 100, and it adds them together and the result back in the accumulator. So the value of the accumulator will change here. So now on to end what we are talking about. So what does this makes this faster or slower? So the biggest bottleneck in the speed difference between the CPU and the main memory, as we discussed in class, is the RAM. So the CPU's cache memory, which is an ultra fast memory located right next to the CPU chip, is crucial Why? Because in this example that we have, if the add 100 instruction and the data 100 also, the both of them are located in the cache, the fetch operation are lightning fast, so the CPU will not gonna wait. And if not, the CPU has to wait for the much slower RAM, causing the delay. And the processor with a larger and smarter cache, he or she, will make the instruction much faster. So, uh, so we know that even for us, the CPU, our computer, our CPU is working really extremely fast. But in reality, inside the CPU, it always have to wait for the memory, for the RAM to get the instruction, to get the data, and this is what may cause the difference between the speed. And finally, a higher clock speed means that the CPU cycle is through this fetch decode and execute more times per second. So that means if we have a higher clock speed, means that the fetch decode execute will be cycles goes more faster and more. We have more cycles per second. So the more we have a clock speed higher, the more our CPU is faster. So here the image is a Samsung launched this jacket the HBM memory in it's a recent, it's a 2025 one, and here is a model how it's going to be in the future, I hope. So for me, why is it most impactful? So first of all, it answers the Moore's law. We can no longer rely solely on transistor shrinkage, making them more smaller. So we're improving the performance by improving the system architecture. That's it. That's the main idea of this. And also, we can relate it to the IOLO age, which is take the multi-core idea to the next level. It's like a multi-core, but it's a multi-chiplet. We're not just using more CPU's core, so we can integrate a CPU chiplet, a high-performance CPU chiplet. Uh, for example, they will be all socket vertically in a 3D structure, like here, and this will drastically reduce the data, drastically reduce the distance the data has to travel. So to make things more realistic, for example, my current CPU has its cores in a single plane. A further chiplet-based CPU could have a memory stacked directly on the top of the core and making the data access incredibly fast, which is instantly fast. So, as I said, this will be just for an application for a faster and faster CPUs. So the thing that makes the CPU slower, as I said, is often the movement of data between two different components, from the memory to the CPU or from the CPU to storage, for example. So this chiplet architecture with these 3D stacks um, will make it more faster, and it will in the future aim to eliminate the bottlenecks by bringing this component physically and electrically closer together. We don't know the risks yet, if it's going to cause more hits or not, but the idea is to make everything closer so that the data will move faster between the component and it avoids the bottlenecks.